What should procurement teams verify before choosing replacing lead-acid emergency light batteries with LEAF-APO4? Key specifications and compatibility risks. The answer is not just speed. Buyers need to check whether the solution fits real production targets, delivers stable data, and reduces downstream risk for quality control, maintenance, and supplier coordination. This walkthrough focuses on the practical evidence a buyer should request before moving forward with a purchase decision. A 7-point replacement check compares 5 voltage platforms, 2 temperature limits, and 6 risks before LEAF-APO4 retrofits. Why emergency light battery replacement is more than a chemistry swap. Replacing lead-acid emergency light batteries with LEAF-APO4 can reduce maintenance pressure and improve long-term service reliability, but it is not a direct chemistry swap in every fixture. Emergency lighting systems depend on battery voltage, charge voltage, discharge cutoff, runtime, enclosure fit, connector layout, and safety documentation. A replacement project that checks only nominal voltage and capacity can still fail when the charger profile, BMS behavior, or temperature limits do not match the original system. The most useful procurement approach is to treat replacement as a compatibility review. The buyer should identify the original battery chemistry, electrical parameters, required emergency runtime, charger behavior, available housing space, expected ambient temperature, and certification requirements. LEAF-APO4 can be a strong replacement pathway, especially in projects that want longer service life and lower routine maintenance. The benefit appears only after the technical risks are verified. 1. The maintenance pressure behind lead-acid replacement. Lead-acid batteries are familiar, widely available, and often inexpensive at the unit level. Aging, sulfation, weight, slower recharge, and maintenance schedules can increase the operational burden for facilities and manufacturers. Emergency lighting products are frequently installed in distributed locations, so each replacement event creates labor cost, inspection time, and potential downtime. 1.1 Cycle life degradation and replacement frequency. A replacement cycle is not just a battery cost. It includes labor, access, testing, documentation, and sometimes customer disruption. If LEAF-APO4 extends service intervals in a validated system, the total cost logic can be stronger than the initial price comparison suggests. Buyers should still avoid assuming that longer cycle life automatically solves system compatibility. 2. Why LEAF-APO4 is considered for retrofit projects. LEAF-APO4 is considered because it can offer long cycle life, stable chemistry, lower weight, and faster recharge potential than many lead-acid configurations. In emergency lighting, these properties are attractive for exit signs, fire lights, and central emergency systems. The retrofit decision should ask whether the selected pack can match the original function without creating charger, BMS, or certification problems. 2.1 Longer service life and lower maintenance frequency. Lower maintenance frequency is valuable only when the replacement pack remains reliable during standby operation. Emergency lights may spend most of their life charging quietly and only occasionally discharging during tests or outages. A strong buying decision depends on more than a good brochure. Teams should compare measurement range, repeatability, calibration method, sample preparation requirements, maintenance support, and evidence from real plant use. When those checks are completed before purchase, the business can reduce retesting, avoid production delays, and choose equipment with more confidence.